2026 AI simulation just proved that Mars almost certainly sent life to Earth. And the math says it wasn't a freak accident. It was inevitable. We've always assumed life started here, that Earth was the origin point, but if Mars was a living planet before Earth finished forming, then everything we think we know about where we came from is backwards.
NASA's Phoenix lander descended to the Martian surface.
30 meters. Touchdown signal detected.
It soon uncovered treasure, frozen water.
In the next 10 minutes, you'll find out exactly what the Davis, Horner, and Carter simulation found, how Martian rocks can travel 140 million kilometers and still carry living passengers, and why NASA's September 2025 discovery just made this the most important scientific question of our lifetime. The hard number, we have already confirmed 277 Martian rocks on Earth. The question nobody's answered until now is whether anything was alive inside them. But here's the part that should stop you cold. The simulation didn't just say the transfer was possible. It calculated that under the impact conditions Mars experienced 4 billion years ago, life-bearing rocks would have reached Earth in as little as 10,000 years. That's a cosmic eye blink. Fast enough for bacteria to survive, and the question the researchers left open, the one that changes everything, is whether the physical evidence already exists in a Martian rock sitting in a NASA lab right now. Mars today is a frozen desert. Minus 60 degrees on a warm day, no magnetosphere worth mentioning, and an atmosphere so thin you'd need a pressure suit just to keep your blood from boiling. Nobody reasonable looks at Mars today and sees a nursery for life. But 4 billion years ago, completely different story. Planetary scientists have known for decades that early Mars had liquid water, not traces oceans, river valleys that stretch for thousands of kilometers, sedimentary rock formations that only form in standing water, carbonate minerals that only precipitate in warm, wet conditions. Mars had rivers, lakes, and almost certainly a global ocean covering the northern lowlands, when Earth was still being hammered into shape by asteroid bombardment. Here's the timeline that matters. Mars solidified and cooled roughly 200 million years before Earth stabilized. 200 million years of head start time. If life can emerge on a warm, wet planet, and apparently it can. Because here we are then, Mars had 2 centuries of geological runway to do exactly that before Earth even had solid ground to stand on. Dr. Paul Davies, the astrobiologist who has championed the Martian origin hypothesis since the 1990s, put it plainly. Mars may have been the original Earth, not a dead planet, a mother planet. Then, 3.9 billion years ago, the solar system went through what geologists call the late heavy bombardment, a period when Jupiter's gravitational wobbles flung millions of asteroids and comets inward. Mars, being smaller and closer to the asteroid belt, took the worst of it. Major impacts arriving every few million years, each one capable of ejecting billions of tons of surface rock into space. Some of those rocks would have drifted toward Jupiter's moons, some toward Venus, and some would have landed on Earth. Could anything survive that journey? And this is what the 2026 AI simulation was built to answer. In May 2026, 3 researchers, Gregory M. Davis, Jonathan Horner, and Bradley D. Carter, published a paper on ArcShift that doesn't exactly scream headline news from its title alone. Could life have been transferred from Mars to Earth? Laboratory and computational simulations of Martian Ejecta. It's the kind of title that gets buried under SpaceX launch updates and NASA press conferences. What's inside it is paradigm breaking. The team built a computational N-body simulation, the same class of gravitational models used to predict asteroid collisions, and used it to trace the trajectories of Martian rock fragments ejected by large impacts. Then, they layered in real laboratory data on microbial survival under the conditions of space travel. Radiation exposure, vacuum, temperature cycling, and the violent shock of re-entry impact. Not one model, a combined framework. Physics plus biology in the same calculation. The result, under the impact conditions Mars experienced during the late heavy bombardment, rocks ejected from the Martian surface would arrive at Earth in as little as 10,000 to 100,000 years. To put that in perspective, that 10,000 years ago, humans were just inventing agriculture. On a geological timescale, that is nothing. That is one eye blink. Here's the number nobody's talking about. We have already confirmed 277 Martian meteorites on Earth. But here's the catch, that's only the ones that fell on Antarctic ice, where dark rocks on a white surface are easy to spot and catalog. The actual number of Martian rocks that have landed on this planet over 4 billion years is estimated in the billions. We're not waiting for the delivery, the package has already arrived. The question is what was inside them? The passengers. Could life survive? Your first instinct is probably, space is lethal. Radiation tears apart DNA. Temperature swings from plus 130 degrees Celsius to minus 270 degrees Celsius within a single orbit. There's no air. The journey takes thousands of years. Nothing lives through that, except that's not entirely true. Certain bacteria called extremophiles are absurdly resistant to exactly these conditions. Think of them as Earth's biological backup drives. Deinococcus radiodurans can survive radiation doses 3,000 times the lethal level for a human. Bacillus subtilis spores sealed inside rock have been tested in the vacuum of open space and survived for years. Tardigrades, the microscopic animals nicknamed water bears, can survive the vacuum, the radiation, and the cold of open space in a state of cryptobiosis. Biological pause mode. The Davis et al. Simulation factored in the survival windows for spore-forming bacteria specifically. And the finding was this: if bacteria were present in the surface rocks of Mars at the time of a major impact, a statistically significant fraction of the ejected material would carry viable life and arrive at Earth before the radiation killed it. Here's where it gets uncomfortable for the skeptics. The team was conservative. They used the lowest published estimates for radiation lethality, the longest plausible travel times, the most violent shock models from laboratory impact experiments. They stacked every assumption against the result. And the simulation still showed successful transfer was not just possible, it was probable. Probable. Not a long shot, not a miracle. The most likely outcome of the physics. The journey, 140 million kilometers. Let's walk through what this journey actually looks like, because the scale is staggering. When a large asteroid 10 kilometers across, roughly the size of the one that killed the dinosaurs, hits Mars at 20 kilometers per second, the impact generates pressures of millions of atmospheres in a fraction of a second. The surface rock around the crater gets launched upward at velocities exceeding 5 kilometers per second. That's Mars's escape velocity. The rocks don't fall back down, they leave. Some enter Martian orbit, some get flung directly toward the inner solar system. A small percentage, the simulation estimates roughly 1 in 10 million rocks, follows an orbital path that intersects Earth. Over 4 billion years of Mars getting hammered by the late heavy bombardment, the numbers add up fast. The rocks travel through space shielded by their own mass. Bacteria buried just 2 meters deep inside a rock receive only a fraction of the surface radiation dose. The journey ends with atmospheric entry, which does heat the surface of the rock, but not the interior. Laboratory studies of Martian meteorites that have actually landed on Earth show their interiors never exceeded 40 degrees Celsius during re-entry. That's cooler than a mild fever. And here's the thing, we've been doing the geology. The most famous Martian meteorite ALH 84001, found in Antarctica in 1984, made international headlines in 1996 when NASA scientist Dr. David McKay claimed it contained fossilized Martian bacteria. The claim is still debated, but the meteorite itself is definitely from Mars. Definitely 4 billion years old. Definitely here on Earth. The rock made the journey. We already know that part works. The Cheyava Falls connection. This is where the timeline becomes electric. In September 2025, NASA announced that the Perseverance rover had found a rock at a location in Jezero crater called Cheyava Falls. The agency described it as, this is a direct quote, "the closest we have ever come to discovering ancient life on Mars." The rock contained organic molecules, leopard spot patterns of chemical compounds that, on Earth, are only produced by biological processes. The patterns matched biosignatures left by microbial mats, colonies of bacteria that live in thin layers along rock surfaces. The kind of bacteria that dominated Earth for its first 2 billion years. Dr. David Kring of the Lunar and Planetary Institute called Cheyava Falls the most scientifically significant rock ever found on another planet. Now put those two things together. Davis et al. Says Mars was almost certainly sending life-bearing rocks to Earth starting 3.9 billion years ago. Cheyava Falls says Mars almost certainly had life 3.9 billion years ago. The overlap is not a coincidence. It's two independent lines of evidence pointing at exactly the same answer. Here's the implication that should change how you think about everything we do in space exploration. If Mars sent life to Earth, it almost certainly sent life elsewhere in the solar system, Europa, Enceladus, Titan. The same N-body simulation framework can be run for any planetary system. The question, is life rare in the universe, just became the question, how often does a single origin seed multiple worlds? We're not asking if life exists beyond Earth anymore. We're asking how many planets received the same starter kit. Let's say the simulation is right. Let's say Cheyava Falls confirms what every astrobiologist has quietly suspected for a decade. Let's say the transfer happened. What does that actually mean for us? It means you are a Martian. Not metaphorically. If the first living cells on Earth arrived inside Martian rocks 3.9 billion years ago, and if those cells were the ancestors of every living thing on this planet, then the entire tree of life, from bacteria to blue whales to you, traces back to a rock that fell from another planet. This is the identity inversion the Hook promised. Not just Mars had life. The story is Mars is life, and that life is US. Some researchers push back. Dr. Kenneth Nielsen at the University of Southern California argues that independent abiogenesis on Earth is equally plausible, that we shouldn't assume a Martian origin just because Mars had a head start. That's fair science. Both could be true life, could have started on both planets, and the Martian version may have arrived here and outcompeted or mixed with what was already emerging on Earth. But here's what Davis et al. Actually changed. Before this paper, panspermia was a hypothesis you had to argue for. After it, panspermia is the default assumption you have to argue against. The simulation shows the transfer wasn't a miracle requiring extraordinary circumstances. It was the expected outcome of ordinary solar system physics. If you ran the simulation 1,000 times, most runs end with Martian material on Earth. The question isn't whether it happened. The question is whether anything inside was still alive. What AI unlocks? Next. The Davis, Horner, and Carter simulation is the first of its kind to combine gravitational dynamics modeling with biological survival probability in one framework. That's the contribution, not just did the rock arrive, but did anything survive the arriving? That framework can now be applied to any planetary system where we observe impacts. It can be run for the TRAPPIST-1 system, where 7 Earth-sized planets orbit within striking distance of each other. It can be run retroactively across a range of impact parameters for the entire early solar system. It opens a new field, computational astrobiology, using AI to map the probability landscape of life spreading through star systems without spacecraft, without intelligence, without intention. It also changes how we interpret data we're already collecting. JWST is cataloging biosignature gases in exoplanet atmospheres right now. If panspermia is efficient, if the Davis et al. Numbers hold up, then biosignatures shouldn't cluster around individual stars. They should cluster around planetary systems groups of worlds where life, once it starts anywhere, spreads everywhere. Carl Woese, the biologist who discovered a third domain of life on Earth, the archaea spent the last years of his career arguing that life is not a planetary accident but a cosmic inevitability. The AI simulation Davis et al. Built suggests Woese was right, and that the next great scientific project isn't finding life somewhere else, it's understanding how connected all of it already is. For 60 years, SETI has been listening for signals from alien civilizations. For 60 years, we've pointed our telescopes outward searching for the other. The Davis et al. Simulation suggests we may have been looking in the wrong direction all along. The alien life we were searching for didn't send a radio signal. It sent a rock. It landed here 3.9 billion years ago, carrying the first passengers on the longest journey in the history of biology. We weren't searching for life on Mars, we were searching for ourselves. Subscribe if stories like this one are why you're here.